Do you know what Newton's biggest regret was before he died? It wasn't that he never married. It was a question he couldn't answer. The Sun is 150 million kilometers from Earth. The space between them is a complete vacuum. So how does gravity travel across it? Does the Sun have a 150 million kilometer long arm? In his book, Newton admitted, "I do not know. Whoever can answer this in the future will be the real genius." 200 years later, a low-level clerk at a Swiss patent office said, "I can." That man was Albert Einstein. His answer completely baffled the whole world. Gravity is not actually a force. The Sun isn't pulling on the Earth, and the Earth isn't pulling on you. The weight you feel right now is actually the floor pushing up against you. You don't get it, do you? That's okay, you'll understand by the end of this video. And from then on, you'll see the world in a whole new way. Our story officially begins over 300 years ago. In 1687, in England, there was a grumpy, lifelong bachelor. A professor who was said to hold quite a grudge published a book. The title of this book was very long. It translates roughly to Mathematical Principles of Natural Philosophy, or just Principia for short. This professor was named Isaac Newton. This book changed the course of human civilization. Newton did something unprecedented in that book. He took the stars in the sky and the apples on the ground, and unified them under the same set of rules. Before him, people thought the heavens were one thing, and the earth was another. They were completely different worlds. The movement of the sun, the moon, and the stars was considered divine and perfect, having nothing to do with the dirt under our feet. Newton said, "That's not right. They obey the exact same laws. An apple falling down, the moon orbiting the earth, follow the same principle. That principle is the law of universal gravitation. Any two objects with mass will attract each other. The greater the mass, the stronger the pull. The further the distance, the weaker the pull. This law is ridiculously simple, yet incredibly powerful. With just this one formula, humanity figured out how planets are bound to orbit the sun, when comets will drop by for a visit, and why the tides rise and fall every single day. Hundreds of years later, they even used it to launch satellites into space and send astronauts to the moon. Newton became a legendary, godlike figure in the scientific world. His theory dominated physics for 200 whole years, and no one could ever shake it. But Newton knew deep down that this theory had one fatal flaw, and it was a flaw he couldn't solve. The problem is this: there are 150 million kilometers between the Earth and the Sun. There is nothing in between, just a complete vacuum. So, how does gravity travel from the Sun to the Earth? Does the Sun reach out with an invisible hand, spanning 150 million kilometers of empty space, to grab the Earth from afar? That sounds way too mystical, doesn't it? What's the difference between that and magic? Newton candidly admitted in his book, "I cannot explain this problem. But the law works." So let's just leave it at that. If someone can explain it in the future, then good for them. See, even Newton just gave up on it. Scientists lived with this puzzle for another 200 plus years. During that time, countless brilliant minds tried to solve it, but all of them failed. Until the decade between 1905 and 1915. When a young man working at the Swiss patent office completely flipped Newton's table over. His name was Albert Einstein. When it comes to Einstein, most people's first thought is that famous photo of him sticking his tongue out. And then, there's that legend about him being bad at math when he was a kid. Let's clear that rumor up first. Einstein was actually always great at math. During his entrance exam for the Swiss Federal Institute of Technology in Zurich, he scored nearly perfect marks in math. That rumor about him being bad at math probably started because he was way too young when he first took the exam. And he failed the humanities section, which led to him getting rejected. Failing humanities got twisted into failing math. Talk about a rough rap to take. Anyway, back to the point. Einstein, back when he was young, really couldn't land a proper job in academia. He was working at a patent office in Bern, Switzerland, as a low-level clerk. His job was to review all sorts of patent applications for inventions. But this guy had a habit. He'd slack off at work to do his own research. In 1905, he published 4 papers in one go. And every single one of them was world-changing. That year is now known as Einstein's miracle year. One of those was on special relativity. And another introduced that famous formula, E equals mc squared. But the coolest part is yet to come. Starting in 1907, Einstein kept obsessing over one problem. Newton's theory of gravity works well enough, but it conflicts with my theory of special relativity. Special relativity says that no information can travel faster than the speed of light. Yet, in Newton's theory, gravity is transmitted instantaneously. If the sun were to nudge, the Earth would feel it immediately. That's impossible. Something must be wrong somewhere. Einstein spent a full 8 years learning a ton of the most cutting-edge mathematical tools of the time, and finally published his general theory of relativity in 1915. The core idea of this theory is, it sounds like the rambling of a madman. Gravity isn't really a force at all. It is the curvature of space itself. I know your head is probably full of question marks right now. Don't rush, let me explain. Imagine this. You take a taut rubber sheet. You stretch it out horizontally. Then, you place a bowling ball on it. The bowling ball is very heavy. It will create a dip in the rubber sheet, right? Now, you roll a glass marble across that sheet. How will the marble move? It will automatically roll toward the bowling ball. Not because the bowling ball is reaching out to pull it, but because the sheet itself is curved. The marble is simply rolling along the curved surface. Einstein said that the universe works exactly like this. The universe we live in is not just an empty box with various objects placed inside. The universe itself is a giant membrane, a four-dimensional fabric of space-time. Massive celestial bodies like the sun, just like the bowling ball, they warp the space-time around them. The Earth isn't being pulled by the sun. The Earth is simply in curved space-time, moving along the most natural path. And that most natural path just happens to be an elliptical orbit. You might ask, then why, when I stand on the ground, does it clearly feel like I'm being pulled by the Earth? At every moment, there is a force dragging me downward. Einstein would say, no, your perception is wrong. The reality is this. Your body actually wants to move downward, following the natural trajectory of warped space-time, falling toward the center of the Earth. But the ground is in your way. That weight you feel. It's actually not the Earth pulling on you. It's the ground pushing you back, stopping you from falling any further. If the Earth were to suddenly vanish into thin air, you wouldn't be pulled toward anything at all. You'd just drift along the natural path of spacetime. You wouldn't feel a single force. It's just like sitting on a train moving at a constant speed. You don't feel any force pushing you back into your seat. Only when the train speeds up or brakes suddenly do you feel a force acting on you. Gravity is exactly the same way. When you're in free fall, you don't actually feel gravity. Astronauts floating around on the space station, the perfect example of this. It's only when the ground stops you from falling that you finally feel your own weight. This theory sounds way too abstract, and it really goes against our intuition. Is it actually true? It's been proven right countless times. Back in 1919, British astronomer Arthur Eddington took advantage of a total solar eclipse to observe starlight from behind the sun shifting its position. That's because the light passing near the sun was bent by the curvature of spacetime caused by the sun itself. This was the very first experimental test of general relativity. Once the news of this confirmation spread, Einstein became a global celebrity overnight. There's been so much more since then, like the unusual orbital movement of Mercury, which Newton's theory couldn't explain, but general relativity explained it perfectly. The clocks on GPS satellites had to be adjusted according to general relativity. Otherwise, your location would be off by several kilometers every single day. You'd end up driving from the 3rd ring road all the way to the 5th. Plus, there are black holes, gravitational waves, and gravitational lensing. All of these phenomena can only be explained by general relativity. This theory has stood the test of over 100 years. It is currently humanity's best understanding of gravity. Alright, after chatting about all these basics of relativity, you might be wondering, what does this have to do with today's topic? I thought you said gravity had nothing to do with mass? It has everything to do with it. The main event is coming up next. According to Newton's theory, gravity is created by mass. If there's mass, there's gravity. If there's no mass, there's no gravity. Simple and clear, no tricks involved. But with Einstein, things get a lot more complicated. Einstein's field equations tell us that it's not just mass that curves spacetime. It's something called the stress-energy tensor. That name sounds pretty intimidating, but the meaning isn't actually that complex. It basically means energy, momentum, and pressure can all curve spacetime. Mass is just one form of energy. Remember that most famous physics equation? E equals mc squared. Energy equals mass times the speed of light squared. This formula tells us an astonishing fact. Mass and energy are essentially the same thing. A tiny bit of matter holds a massive amount of energy. That's the principle behind the atomic bomb. Conversely, a large enough amount of energy can behave just like mass. That's how they create new particles in particle accelerators. Mass is just one form of energy, just like ice is just one form of water. Ice can melt into water, and water can freeze into ice, but they are essentially both H2O. Mass can be converted into energy, but at their core, they are the same thing. So what does this mean? It means that since spacetime curvature responds to energy, and mass is just one form of energy, then other forms of energy should be able to curve spacetime too, and create gravity. The answer is, of course they can. Let's start with light. In our daily lives, light feels like something intangible and weightless. It illuminates the world, warms your skin, yet you can't grasp it, nor can you weigh it. But does light have energy? Of course it does. When sunlight hits your face, you feel the warmth. That is the energy of light heating up your skin. Plants use photosynthesis to turn sunlight into chemical energy, storing it in sugars. Solar panels convert light into electricity. Light definitely has energy. So, does light have mass? That is a bit of a subtle question. Photons, the fundamental particles of light, have no resting mass. You can't just hold a photon down and put it on a scale to see how much it weighs. Because photons are always on the move. They always fly at the speed of light, never stopping for a second. However, photons have energy and momentum. According to relativity, energy and mass are equivalent. So, in a sense, light also has equivalent mass. Right, so since light has energy, can light curve spacetime and create gravity? Yes, 100%, it can. This isn't just some theoretical guess. It's a direct deduction from Einstein's equations. If a beam of laser light flies past you, it will cause the surrounding spacetime to curve ever so slightly. Of course, this curvature is almost impossible to measure. The light in our daily lives is just way too weak. But in principle, it is absolutely there. What if you could increase the intensity of light to an extreme degree? Theoretically, if you could take a powerful enough laser beam and cram it into a small enough space, the curvature of spacetime it creates would be so intense that it could trap light itself, forming a black hole made entirely of light, with no matter whatsoever, and no mass in the traditional sense. Just pure light, yet it generates a powerful gravitational pull. That sounds insane, right? But the laws of physics say it is entirely possible. It is just that we currently lack the technology to achieve it. There is another, more grounded example. If you trap light inside a box with perfect mirrors, letting the photons bounce around infinitely inside, the box would become heavier. Not just a tiny bit heavier, but heavy enough to be measured. The more light there is in the box, the heavier the box becomes. Why? Because trapped light has energy. And energy curves spacetime. Curved spacetime is gravity, manifesting externally. It is as if the box has gained weight. You are not filling the box with sand or iron balls, with light. Yet the gravity of that box has undeniably increased. Light does not have mass in the traditional sense, but light does have gravity. This is the first example of gravity without mass. Okay, light can generate gravity. That is already mind-blowing enough. But there is something even more groundbreaking coming up. Pressure can also generate gravity. You might say, pressure, is not that just things being squeezed together? What is so strange about that? The strange part is, it is not just the matter creating the pressure that has gravity. It is the pressure itself that curves spacetime. This sounds too mystical. Let me use a star to give you an example. A star, like our sun, is essentially a massive sphere of plasma. Its mass is incredibly huge, and its own gravity is frantically trying to crush all its matter toward the center. So why hasn't the sun collapsed into a tiny point? Because at the sun's core, nuclear fusion is taking place. Hydrogen nuclei fuse together, releasing a tremendous amount of energy, and generating intense heat and pressure. This outward pushing pressure balances out the inward pulling gravity. That is why the sun has been able to burn steadily for billions of years. Up to this point, it is all common knowledge. But the next part gets a bit strange. According to Einstein's theories, that outward pushing pressure is actually increasing the sun's gravity as well. Wait a minute, isn't that a contradiction? The pressure is fighting against gravity. Yet at the same time, it is strengthening it. It is not a contradiction. In general relativity, pressure is a form of energy. And any form of energy warps spacetime. So, the greater the pressure, the more severely spacetime is warped, and the stronger the gravity becomes. This leads to a magical effect. The harder you push back against gravity, the more you actually strengthen it. In an ordinary star, this effect isn't very noticeable. But in some extreme celestial objects, it becomes incredibly important. Take a neutron star, for example. Which is the remnant left behind after a massive star dies? Just how dense is it? A single spoonful of neutron star matter weighs about several 100 million tons. Matter the size of an entire city is compressed into a tiny sphere only about 20 kilometers in diameter. The reason a neutron star has such terrifying gravity is not just because of its high density. It's also because the internal pressure reaches an incredible level. That enormous pressure, which resists gravity and stops the neutron star from collapsing further, is simultaneously making the neutron star's gravity even stronger. It's a self-reinforcing effect. The higher the pressure, the stronger the gravity, which then requires even more pressure to resist it. When this cycle spirals out of control, the neutron star will continue to collapse until it becomes a black hole. So, you see, pressure isn't just a simple matter of matter squeezing together. Pressure itself is a form of energy. It can warp spacetime, and it can generate gravity. Alright, at this point, we've already identified 3 things that can generate gravity: mass, light, and pressure. They share a common trait. They all involve something existing. Mass is matter, light is photons, and while pressure is invisible, it still requires something to create it. So, that leads to a question. Is there any situation where there is nothing at all, yet gravity still exists? Well, actually, there is. This is one of the most astonishing discoveries in modern cosmology. The void itself has weight. I know that sounds like a Zen koan. Like the metaphysical concept of form is emptiness, emptiness is form. But this isn't just philosophical speculation. It's a scientific fact supported by observational evidence. The story begins with a mistake made by Einstein. In 1917, Einstein applied his field equations to the entire universe, trying to calculate the fate of the cosmos. At the time, everyone, including Einstein himself, was convinced that the universe was static, eternal and unchanging. The universe is just there, neither increasing nor decreasing. From the past to the future, it remains exactly the same. But Einstein's equations produced a conclusion that absolutely shattered him. The universe cannot be static. It is either expanding or contracting. Either way, it's impossible for it to just sit still. Einstein didn't buy it. He felt there must be something wrong with the equations. So, he did something scientists usually shouldn't do. He forced an extra constant into the equation, artificially pinning the universe down to keep it still. He called this constant the cosmological constant. If the universe really were static, that move might have made sense. The problem is, the universe isn't static. More than 10 years later, American astronomer Edwin Hubble, using the largest telescope in the world at the time, observed those distant galaxies. He discovered a staggering pattern. The spectra of almost all galaxies were redshifted. This meant they were all moving away from us. And the farther away a galaxy was, the faster it was moving. There was only one conclusion: the universe is expanding. When the news reached Einstein, he was deeply frustrated. It is said that he called that cosmological constant the greatest blunder of his life. If he had just trusted his own equations back then, he could have predicted the expansion of the universe before Hubble, and become the first person to predict the fate of the cosmos. That would have been a Nobel Prize-level achievement. And he threw it away with his own hands. But the story doesn't end there. Nature had a belated surprise in store for Einstein. In 1998, 2 independent teams of scientists, while studying distant Type 1a supernovae, discovered something incredibly strange. What they wanted to measure was the deceleration rate of the universe's expansion. Theoretically, all the matter in the universe should be pulling on each other with gravity. The expansion ought to be slowing down over time. It's just like throwing a ball up into the sky. The ball slows down because of Earth's gravity, and eventually falls back down. What they wanted to find out was just how fast this cosmic ball was slowing down. But when the results came back, everyone was completely stunned. The universe wasn't slowing down. The universe is actually accelerating. The expansion isn't getting slower. It's getting faster and faster. It's like throwing a ball out. And instead of slowing down, it just keeps flying faster and faster. It completely defies intuition, defies Newtonian physics, and seems to defy all common sense. Unless there is something we cannot see pushing the universe outward. Scientists gave this mysterious thing a name: dark energy. Dark doesn't mean it's literally black. It just means we cannot see it. We cannot detect it, and we have no idea what it actually is. We can only infer its existence through its gravitational effects. So, what exactly is dark energy? The most widely accepted theory right now is that it is the energy of the vacuum itself. You might think a vacuum means there's absolutely nothing there. So how could it have any energy? But quantum mechanics tells us that a vacuum is not actually empty. Within a vacuum, there are intense quantum fluctuations happening at every single moment. Virtual particles are constantly popping into existence in pairs, and then quickly annihilating each other. It's one after another, never stopping, never resting. These fluctuations carry energy. The vacuum itself has a baseline energy density. It's not zero, but a positive value. This vacuum energy has a very peculiar property. It doesn't get diluted as space expands. Ordinary matter gets diluted. If you put a box of gas into a larger box, the gas density drops. As the universe expands, the density of matter decreases. But vacuum energy doesn't work that way. If space expands by double, the total amount of vacuum energy also doubles. Because every bit of new space comes with its own vacuum energy. What does this mean? It means the larger the universe expands, the more vacuum energy there is. And this vacuum energy generates a kind of negative pressure, pushing space to keep expanding. The larger the space, the stronger the push, and the faster the expansion. It's a positive feedback loop of self-acceleration. Current observational data tells us that the total energy of the universe is roughly distributed like this. Ordinary matter, the stuff made of atoms, including you, me, the Earth, and the stars, accounts for about 5%. Dark matter, a mysterious substance we don't know the nature of, which only interacts with ordinary matter through gravity, accounts for about 27%. And dark energy, this weight of the void, accounts for about 68%. You read that right. Nearly 70% of the universe's energy comes from absolutely nothing. This is one of the most ironic discoveries in the history of physics. We once thought matter was everything, and the void was zero. It turns out the void is the main character, and matter is just a supporting role. Moreover, this void isn't just existing. It's actually determining the ultimate fate of the universe. If it maintains its current strength, if the rate stays the same, the universe will expand forever. Every galaxy outside our own local group will drift further and further away. The speed of this expansion will exceed the speed of light. That's right, the expansion of space itself can be faster than light. And so, those distant galaxies will gradually vanish from our view. We'll never be able to see them again. Stars will burn out, one by one. It will become harder and harder for new stars to form. Black holes will slowly evaporate through Hawking radiation. In the end, the entire universe will turn into a cold, dark, empty void. And this void will just keep on expanding endlessly. Physicists call this the heat death. Sounds pretty hopeless, doesn't it? But what if dark energy gets stronger over time? Then things would get much more dramatic. The expansion would accelerate and accelerate again, eventually becoming so violent that even galaxies, stars, planets, molecules, and atoms would be torn apart. Every structure would crumble away into the expansion. Physicists call this the Big Rip. It's a much more brutal kind of cosmic apocalypse than the heat death. And what if dark energy grows weaker over time? Then the expansion might slow down, stop, or even reverse. The whole universe would start to shrink. Everything would get closer and closer, until it finally collapses into a single point. Maybe it would trigger a new Big Bang. Or maybe it would just be the absolute end. Physicists call this the Big Crunch. You see, the void isn't just nothing. The void is the master of everything. The fate of the universe is written in the weight of the void. Alright, so far we've covered how light, pressure, and even the void can create gravity. But there's one more, the purest form of gravity with no mass at all. You've probably heard of it in the news. That is, gravitational waves. September 14, 2015. At 9:50 Greenwich Mean Time. A signal that traveled for 1,300,000,000 years has finally reached Earth. It originated from the distant depths of the universe. Two massive black holes, one with 36 times the mass of the Sun, and one with 29 times the solar mass, were engaged in a dance of death. They had been orbiting each other for untold billions of years. Their orbit growing closer and closer. In those final moments, they circled each other at nearly half the speed of light, and then violently crashed together. Merging, they became a single, even larger black hole with 62 times the mass of the Sun. Wait a second, 36 plus 29. Isn't that 65? How did it become 62? Where did those three solar masses go? The answer is that they transformed into pure energy, released in the form of gravitational waves. Just how massive is the energy of three solar masses? It is roughly 5 times 10 to the power of 47 joules. That number is so huge. It's hard to even wrap your head around it. Let's put it another way. In those few fractions of a second during the collision, the energy released by these two black holes was more than all the light emitted by every single star in the entire observable universe, combined at that very same moment. Where did all this energy go? It didn't turn into light. It didn't turn into heat. It didn't turn into any kind of particles. It turned into ripples in spacetime itself, gravitational waves. You can imagine throwing a stone into a calm pond. Ripples spread out in every direction. Gravitational waves are just like that. Only it's not the surface of the water rippling. It is spacetime itself. Spacetime is being stretched and compressed. This stretching and compressing vibration travels outward at the speed of light. These ripples traveled across a distance of 1,300,000,000 light-years. Back then, not even multicellular life had appeared on Earth yet. Finally, at the end of 2015, they reached our solar system. As they pass by Earth, they stretch and compress space itself. In one direction, it gets stretched out, while the perpendicular direction gets squeezed. Then, it alternates back and forth. Humans use a precision instrument called LIGO to detect these changes. So, what is LIGO? It consists of two massive L-shaped vacuum tunnels. Each tunnel is 4 kilometers long. Lasers bounce back and forth inside the tunnels to measure the changes in the tunnel's length. When a gravitational wave passes through, just how much does this 4-kilometer length change? About 10 to the power of minus 18. That is 0 point, followed by 16 zeros and a1 centimeters. What kind of scale is that? A proton's diameter is about 10 to the power of minus 15 meters. So, the change LIGO detected is roughly 1/1000th the diameter of a proton, over a distance of 4 kilometers. Measuring the change of 1/1000th of a proton's diameter. This level of precision is equivalent to measuring the distance from Earth to the nearest star, with the accuracy of a single hair's width. Humanity really is incredible, but more importantly, what does this discovery prove? Gravitational waves themselves have no mass. They are not particles. They are not matter. They are spacetime itself. Geometric vibrations. It is pure curvature traveling through space. Yet, they carry immense energy. Energy equivalent to 3 solar masses traveled for 1.3 billion years. And after 1.3 billion light-years, it shook mirrors here on Earth. This is the most direct evidence that gravity does not require mass. Spacetime itself can vibrate and transmit energy, all without the involvement of any matter. Gravity has broken free from its source, traveling through the universe all on its own. Since that first detection, scientists have heard it dozens of times. Gravitational wave events. Each one is a whisper from the depths of the universe. Black hole collisions, neutron star mergers, stellar collapses. These extremely violent cosmic events cannot be observed with light at all. They can be detected with gravitational waves. Gravitational waves tell us where heavy elements like gold, platinum, and iridium come from. They were forged In the fiery heart of neutron star collisions, gravitational waves tell us that the black holes in our universe are more numerous and larger than we ever imagined. Gravitational waves allow us to see things that can never be seen with light. Before this, humanity could only observe the universe through electromagnetic waves. From radio waves to gamma rays, they are essentially all light. Now, we can finally listen. It is like someone born deaf suddenly gaining the sense of hearing. The entire world becomes completely different. Alright, let us return to the initial question. Without mass, can gravity still exist? Now we can answer with confidence. Absolutely, it can. Light has gravity, because light has energy, and pressure has gravity, because pressure is a form of energy. The void has gravity, because the vacuum itself contains energy. Gravitational waves themselves have no mass. It is gravity in motion, a pure ripple in spacetime, carrying energy as it travels across the universe. But having said that, this does not mean that mass is unimportant. Mass remains the absolute protagonist of gravity. The weight you feel comes from the 6 sextillion metric tons of mass in the Earth. The Earth orbits the Sun because of the 2 nonillion metric tons of mass in the Sun. The hundreds of billions of stars in the Milky Way are held together also thanks to mass, including the mass of the dark matter we cannot see. In these scenarios, gravity from light, pressure, or the vacuum are all so small they can be completely ignored. Mass stands alone as the dominant force, governing almost everything we can observe regarding gravitational phenomena. So, the knowledge you've learned that mass creates gravity isn't wrong. It's just incomplete. The complete statement should be, energy creates gravity. Mass is just the most common and intuitive form of energy, but it's not the only one. Einstein's genius lies in the fact that he revealed this deeper truth. Spacetime doesn't care what form your energy takes. Whether it's mass, light, pressure, or vacuum energy. As long as you have energy, spacetime will curve to respond to you. From this perspective, mass isn't actually anything special. It's just energy, wearing the outfit we recognize the most. So, what exactly is gravity? It isn't a force. It's not an invisible rope tethering you to the Earth. It is the shape of spacetime itself. It is the geometric projection of energy. It is the way the universe tells all things how to move. When you are sitting in a chair, your body wants to follow the curvature of spacetime downward. But the chair gets in your way. When the Earth orbits the Sun, the Earth is simply moving along the path of spacetime curved by the Sun. When light bends as it passes by a massive celestial body, that's just light following the shortest path through curved space. When gravitational waves travel through the cosmos, that is the shape of spacetime itself, propagating like ripples on water. Behind all these phenomena lies the same principle. Spacetime is curved by energy, and everything moves along the curvature of that spacetime. This is the universe that Einstein saw, a universe that doesn't need forces, a universe where energy shapes geometry, and geometry guides motion. A universe where even light, pressure, and nothingness can produce gravity. Which brings us to this. You might ask a very imaginative question. Could we humans create gravity ourselves? Not by piling up mass, but by using light, by using energy? Theoretically, absolutely. If you could focus a laser strong enough into a tiny enough space, you could create measurable spacetime curvature. If you could control how vacuum energy is distributed, perhaps you could manipulate gravity itself. The artificial gravity weapons, and warp drives from sci-fi novels don't actually violate the laws of physics in principle. But in reality, it's harder than reaching the heavens. So hard that it might never be achievable. To produce even the tiniest bit of detectable gravity, the energy density required is completely beyond our current technological capabilities. The gravitational effect produced by our most powerful lasers is less than that of a speck of dust. To reach a practical level, the energy needed might be more than the total output of the sun. But then again, people 100 years ago couldn't have imagined that we'd be making video calls on phones today, using satellite navigation, or detecting gravitational waves from 1.3 billion years ago. Who knows? Maybe a few hundred or a few thousand years from now, humanity will truly learn to manipulate spacetime, and be able to create gravitational fields using pure energy. When that day comes, interstellar travel might no longer be science fiction. But until that day arrives, we can at least remember this profound truth we learned today. Gravity does not belong to mass. And energy is the shared essence of everything that exists in the universe. Light is energy. Matter is energy. Motion is energy. Heat is energy. Even nothingness. The vacuum itself is also energy. Spacetime listens to all their voices and bends itself in response. This is the true face of our universe. It's not an empty box, filled with some matter, but a living curtain, shaped by everything upon it, including the lights, and even the stage itself. Whether you are sitting, standing, or lying down scrolling through your phone right now, the floor beneath your feet is pushing back against you, resisting the curvature of space-time that wants to pull you down. You think it's the Earth pulling you, but in reality it is the geometry of the entire universe telling you, friend, this direction is called down. If you ever get the chance to look up at the night sky, just think, every beam of starlight is subtly curving space-time. Every burning star is rewriting the geometry of the universe with its light and heat. Distant black holes are colliding, and gravitational waves are traveling across billions of light years to reach you. And that vast, expansive void between galaxies is pulling the entire universe apart with the weight of its nothingness. All of this is gravity. All of this doesn't require what we traditionally think of as mass. All of this only requires one thing: energy. And energy is everywhere. So, gravity is everywhere, too. We just didn't realize it before. Alright, that's where we'll wrap up today's story. From Newton's apple to Einstein's space-time. From the weight of a photon to the gravity of the void. From the ripples at LIGO to the destiny of the universe. This journey has spanned over 300 years of physics history. I hope that next time you feel a sense of weight, you'll think back to today's story. And remember that it isn't the Earth pulling on you, but rather, space-time guiding you. Remember that gravity isn't just a property of mass, but the language of energy. If you found this insightful, don't forget to like, follow, and save. Hit that triple tap for me. Your support is the fuel that keeps me making these science videos. I'll see you in the next one. Oh, and one last question to leave you with. If even nothingness has weight, then does the concept of having absolutely no weight at all even exist in this universe? If it does, what would that even be? And if it doesn't, what does that imply? That question is for you to think over yourself.